Hi everyone, many thanks for coming to check out our poster. Along with my colleague Megan Owen, I'll provide a very brief overview of the present study, which builds upon work that we've reported previously on how visual short-term memory resources are allocated to visual information. So in this previous work, we embedded a change detection task within a task switching paradigm, wherein the goal was to determine whether a change in either color or orientation occurred between two stimulus displays. A consistent finding from the task switching literature is that when there's a requirement to switch between performance of multiple tasks, both errors and response times are increased compared to when the same task is repeated. So the results from our previous work follow these findings, showing that performance is negatively impacted on this change detection switching task when there's a requirement to switch between which feature dimension is attended to compared to when the feature dimension repeats. But it should be noted that this detriment to performance is only observed when a change in the irrelevant feature dimension also occurs, thus making the Q essential for correct performance of the task.
In the present study, we attempt to differentiate between two prominent theories of switch costs, the task set inertia and the task set reconfiguration accounts. On the task set inertia account, it is believed that switch costs arise due to interference from the previously relevant task set, while on the task set reconfiguration account, it is believed that switch costs are a result of the process of activating the newly relevant task set. By manipulating the duration between response on one trial and the presentation of the Q on the subsequent trial, the response Q interval, we can manipulate the impact of task set inertia. Increasing this duration should allow more time for the previously relevant task set to dissipate, thus leading to reduced switch costs. Likewise, by manipulating the duration between presentation of the Q and presentation of the stimuli on the same trial, the Q stimulus interval, we can manipulate the impact of task set reconfiguration. Increasing this duration should allow more time for the activation of the newly relevant task set, thus leading to reduced switch costs. In the present study, we used long and short Q stimulus and response Q intervals, with the long interval being 900 milliseconds and the short being 100 milliseconds. Only mixed blocks were used within this experiment, meaning participants either performed dimension repetitions, for example, a colour trial followed by a colour trial, or dimension switches, for example, a colour trial followed by an orientation trial.
While overall switch costs were found for accuracy, comparison of the switch cost values for long and short trials revealed no substantial evidence to suggest that manipulation of the response Q or Q stimulus intervals had any impact on switch costs in this task. So this clearly deviates from what would be expected based on the task switching literature, and future research may benefit from manipulations that account for the interplay between inertia and reconfiguration as a possible means to understanding the origin of switch costs in this dimension switching task. Complete raw data and analysis scripts for this study are available on the OSF by either scanning or clicking the QR code at the top of the poster. Thank you very much for listening.